learners, welcome back to Soundarya Study Zone. Today we are diving into the most basic concept of theory of computation, and they are symbols, alphabets, strings and languages. Okay, so these are all the four basics of theory of computation. So at first, what is symbol? So remember, it is symbol, right? So a symbol is the most basic unit in theory of computation. So it is a single character. So for all these things, base is symbol. Okay. So a symbol is the most basic unit in theory of computation, which means it is a base for alphabet, strings and languages too. And then it is a single character. Remember this one, it is a single character that can be used to form strings. So here we have strings, right? So this is what we are going to discuss next. So symbols are used to form, or it is a single character that can be used to form strings. Okay, and then we have symbols. We can represent symbols like A, B, Z, 0, 1, hash, dollar, or we can say like star, or here there is a boy and we can represent it as a girl. Anything can be used to represent a symbol. Okay, so these symbols do not have meaning by themselves, right? So if we can write A equals to something, let's take like this. If there is nothing here, then there will be no meaning for this one, correct? So it has no meaning by themselves, but if they combine or brought up together, they have meaning. This is the basic thing about symbols. Okay, so we are done with symbols. Symbols is done. Now we are going to the alphabets. So what is an alphabet? So an alphabet is a finite non-empty set of symbols. Remember this one, symbol means it can be A, correct, or B or 0. It can be anything, right? So finite non-empty set of symbols. Symbol means only one letter, right? A is a symbol, B is a symbol, 0 is a symbol, like that. So finite non-empty set of symbol is called as alphabet. So we denote it by, what is this? This is sigma. So this is a Greek letter. Okay, so we denote alphabets by sigma, and this is a Greek letter. Okay, and then we have sigma equals to, so we should have finite non-empty set. Non-empty set, which means here there should be something inside it. Something means there should be symbols inside it, correct? So here there are elements like 0, 1, 2, A, like that. So 0, 1 we represent it as a binary symbol. Okay, it is a binary symbol, and here A, B, C is an English subset, correct? It is an English subset. So here we can have like this also. Okay, combination of these symbols or numbers and alphabets. Here this is the combination, and here we can have this combination also. So what is this? This is sigma, and it is a Greek letter. So we represent alphabet by sigma. So alphabet is a non-empty finite set. We can't write it like 1, 2, so on, because it is a finite set. So it can be 1, 2, 3, like that only. Okay, so this is about alphabet. Okay students, now we are done with symbols and alphabets, correct? Now we are done with symbols and alphabets. Now we are moving to strings, correct? So what is a string? A string is a finite sequence of symbols from an alphabet, that is sigma, correct? A string is a finite, which means it is a readable number of terms or countable number of terms. So it is finite sequence of symbols formed by an alphabet Z. So symbols means it is an individual term like A, B, C. Alphabet can be A, B, right? 0, 1. So here we are forming a finite sequence of symbols from alphabet. From the alphabet we are creating a sequence of symbols. Sequence, which means we are shuffling out like that. Okay. So here so what we have to take? With the help of alphabet we are taking the sequence of symbol, correct? So we have this sigma equals to 0, 1. This is an alphabet. You can find out it, right? This is an alphabet. So from this we have to derive a string. So here strings are, so how we can form is, so I hope you understand what is sequence of symbols, right? Which means we are creating some kind of mismatching or matching out the symbols, correct? So look here there is 0, 1. So we can write it like 0, 1, 0, 0, 1, 0, 0, 1, 1, or we can write it like 1, 1, 1, 0, 0, like that. Okay, this is a combination of symbol taken from the alphabet. Here there is no A, right? We can't write it like A1. This is wrong. Okay, from the alphabet we are taking out the string. And another example is from sigma. We have an alphabet A, B. From that we are taking out the symbol. So here A, B, B, A, B. We can write it like B, 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 A, and so on, right? So this is about string. Okay, I hope you understand about symbol, alphabet and string, right? So there are some basic or important terms in strings, and they are, first one is empty string. So empty string is represented by epsilon. Okay, this is epsilon. Empty string is represented by epsilon. So epsilon equals is a string with no symbol. Empty string, a string with no symbol, correct? And then we have length of a string. So what is the length of this string? How to find it? That is number of symbols in it. This is the length of a string. So here we have A, B, B, A. What is the length of this string? We have 1, 1, 1, 1. That is 4 letters. So we have length of a string as 4. Here length of a string is 1. Here 2. Here also 2. Here 1, 2, 3, 4. Sorry, 4. Correct? 1, 1, 2, 3, 4. 4. 1, 2, 3. 3. Here only 1, 1, 2, 3. Is it clear? This is how we find length of a string. So this is about string. Okay. Okay, we have seen about symbols, alphabets and string. Now let us go through the next topic, that is powers of an alphabet. So we have alphabet, right? So what is the power of an alphabet? So it is represented by, how to represent alphabet? With the help of sigma, correct? So how to represent power of alphabet? With the help of sigma to the power 0, sigma to the power 1, sigma to the power 2, so on. Okay, so if sigma is an alphabet, then sigma to the power k denotes the set of strings of length k. Remember this one, sigma to the power k denotes the set of strings of length k. Okay, so here we have epsilon to the power 0. So let us take one example. Okay, so epsilon to the power, sigma to the power 0 will be epsilon, correct? Which means sigma to the power 0, nothing. And then sigma to the power 1 means all strings of length 1. Okay. Sigma to the power 2 means all strings of length 2. So let us take this example. Okay. So for sigma equals to a comma b, we have, let's take the powers from 0, 1, 2, so on. Okay. So sigma to the power 0 is empty string, and then sigma to the power 1 from AB is strings of length 1. We can write it like A and B. Is there any other term of length 1? No, right? We can write A, B, that's it. So sigma square, that is combination of A, B. So whatever the combination we can do, A, done, AB, done, BB, done, and then BA, done. Is there any other possible way that is left? No, right? So this is how we represent the powers of an alphabet. So if we take sigma cube, it will be like A, B, A, B, and then B, is there anything left? I don't know. If there is anything left here, please do comment in the comment section the things that are left. Okay. So likewise we have to represent the power of an alphabet, which means basically a length of string which is in the length of K. Okay. That's it. That is the power of an alphabet. Okay, we are done with symbols, alphabets, strings, power of an alphabet. Now we are moving to the string concatenation. Now we are very clear with the strings, correct? So now how to concatenate, combine two strings. Okay, that is string concatenation. So string concatenation means joining two strings. Remember this, joining two strings end to end. Okay, joining two strings end to end means string concatenation. So if x equals to a comma b, this is the example. Okay, if x equals to ab and y equals to ba, then how to represent concatenation? Like this. Okay, x concatenate with y, or x dot y equals to ab, this is a term of x, with B, A. This is the string concatenation. Okay. So other thing is concatenation is not commutative. So here AB plus BA is not equals to BA plus AB, because here simple thing is AB is not equals to BA, right? Because this is an individual element, this is individual, this is individual, this is individual. So here we can, here string concatenation is not commutative. So these are all the things we have studied. So in the next video, let us go through the clean operators and languages. Okay, until then, bye bye.